Hello class, I thought I'd go on and develop a video for the first part of chapter 9, which is the last material that we cover in this course. So we're really changing gears here. Chapter 9 was used for nuclear medicine program that we used to have. We also, I think it's a good introduction for those of you thinking about being a radiographer. And it's also important for those other allied health majors to know just a little bit about radiation. So we're going to talk mainly about the components of radiation, and we'll look at predicting decay products, and that's all we're going to cover in chapter 9. We're not covering nuclear reactors or the rest of the chapter. So it's a short chapter. I think it's manageable. I think it's a great chapter for you to read, comprehend, and do well on the module. It is on the final exam, and it is on the last exam of the semester. So I think this is an opportunity to master this small amount of material and boost your grade here at the end of the semester. So radioactivity is the process in which an atom decays, falls apart, and when it falls apart, it releases a radiation, which is energy from a point source. So when that atom falls apart, and the protons and neutrons separate, then we will have a release of energy, which we call radiation. So radiation just means, let's define what radiation is. It just means energy from a point source. So when they say radiation, the particles or rays emitted come from the nucleus. That is the point source. So in order to indicate radioactive decay, we have to know the atomic symbol, atomic number, and mass number. These are things we've already learned in this class, so this is going to be a little bit of a refresher. The atomic symbol is what we see on the periodic table that represents a group of atoms that have the same number of protons. The atomic number represents the number of protons in that particular atom or element. So when we're looking at boron here, we know that boron has 5 protons, and that all boron atoms in the entire universe have 5 protons. So that number 5 in the bottom left hand corner represents the number of protons. The 11 represents the protons and the neutrons, and that's called the mass number. So you need to know mass number is always going to be a whole number. It's a counted number. It is the number of protons and neutrons in the nucleus. The atomic number, again counted, it's 5 here. When we subtract the atomic number from the mass number, we get the number of neutrons. So you'll need to be able to do that to label this correctly. This is called an isotopic symbol. We've had this previously in a previous chapter. Isotopic symbols have mass number in the upper left-hand corner. They have atomic number in the lower left-hand corner, and then you have the chemical symbol. Sometimes you will not see the atomic number because they know if you know the chemical symbol, then you know what the atomic number should be, or at least you can look it up on the periodic table. So again, this is an isotope. The protons define the element, and another name for this is the nuclide. So in nuclear chemistry, if you hear the word nuclide, that's what they're talking about. Okay, nuclear chemistry, often called a nuclide. This is not the only isotope of boron. And the way we speak this is called boron 11. So we speak it as boron, the element's name, dash, and the number, which represents the mass number. So boron has an average atomic mass that we look on the periodic table of 10.811. 1 atomic mass units. That's how much one boron weighs, or more. That's how much the average atomic mass for boron is. So that tells us that if there are two isotopes of boron, if there's a boron 10 and there's a boron 11, because this number is closer to 11 than it is 10, we know this one occurs the most in nature. We talked about that when we talked about relative abundance. I think it's like chapter 2. We talked about atomic mass units and how that's defined, that atomic mass unit is 1/12 of a carbon-12 atom. So again, this is nothing new here. And hopefully it's just a refresher. When we look at boron 10, because this would be a 10, the 5 does not change because that would change the element. So 10 minus 5, boron 10 would have 5 neutrons. So it would have 5 protons and 5 neutrons, where boron 11 has 6 neutrons. It weighs a little bit more. So that's what a neutron does. A neutron makes an atom weigh a little more than something that has less neutrons, or an isotope that has less neutrons. Let's say that. So here we have the 3 isotopes of carbon. So there's carbon 12, which this one would have 6 neutrons. There's carbon 13, which would have 7 neutrons. And there's carbon 14, which would have 8 neutrons. So the only difference, chemically, you cannot tell the difference between these. They all have a total of 6 electrons. They have 4 electrons in the outer shell. You guys, we've done the Lewis dot symbols, and we know it has 4 valence electrons, and that is what is involved in a chemical reaction. But what we're focused on is the nucleus, and the nucleus has the protons and neutrons, and the more neutrons a particular nucleus has, the more likely it is to be radioactive, and the heavier it is. So again, speak the language: carbon 12, carbon 13, carbon 14. So some isotopes are stable and some are not. So the ones that are unstable are the ones that produce radioactivity. And we're going to write nuclear equations, and we're going to use chemical isotopic symbols, and we're also going to talk about the types of radiation that can be emitted from the nucleus. So alpha particles, beta, positrons, and gamma rays. Each one of these is going to have its signature, and that will help you indicate what type of radioactivity we're dealing with. So you'll see a change in the isotopic symbol based on which one of these components is released. So that's what we're going to focus on the rest of this chapter, is being able to write a nuclear equation that represents an alpha decay, a beta particle, a positron, or a gamma ray. So the first one is the alpha particle. The alpha particle is similar to a helium nucleus. It has a mass number of 4. You say, how did you get that? Well, 2 protons, 2 neutrons. Protons plus neutrons equals mass number. So a mass number of 4. It has an atomic number of 2. And atomic number 2 represents the symbol helium, the chemical symbol helium. It's got a 2 positive. There's no electrons. So that's there's a couple differences here. Alpha particles have a different energy than helium, and alpha particles do not have any electrons. So to show that it doesn't have electrons, sometimes people put a 2 positive charge, like you see with this. But most of the time it's written this way, or by just the symbol alpha. So alpha particles are slow moving. They can be stopped by small barriers like paper, plastic, and things like that. We've seen alpha particle before. This is what Rutherford fired into the gold foil, and he thought those alpha particles, having this mass, they would go right through the gold foil, and because he knew it's a lot more massive than an electron. So he thought he'd go right through the foil, no problem. But what he found out was some were deflected, some were reflected. So he knew that there was something massive in the center of an atom, which we found out to be the nucleus. All right. And then Chadwick discovered the neutron that's also located in the nucleus. The next particle is called the beta. So beta, what makes it different is it doesn't have a mass number. So it has 0 mass. It has a -1 charge. All right. And you say, what is that? How did that come about? Well, it's when a neutron is converted to a proton. So a positive charge leaves from the neutron, and this is what we have left over. They're higher speed particles than alpha particles, and they have more penetrating power than alpha particles. But they can be stopped with a fair amount of glass or plastic. They definitely can be stopped by water and concrete and things like that. But they are fast moving, and a lot of people say they're a fast moving electron. But here's what I want you to remember. This is important. It's not an electron from the shells around the atom. It's not an electron from the shells. This electron comes from the nucleus. And it comes from the nucleus when a neutron is converted to a proton. All right? So that neutron loses a beta and becomes positively charged. And we call it a proton then. So you say, why do I need to know all these symbols? Well, this is the most common, but that's not helpful when you're doing trying to balance a nuclear equation. This is probably the most helpful when you're working on problems. And you can see this is a high energy electron. That's what they say. It's kind of hard sometimes to say, oh, beta means high energy electron. So starting out, I think this symbol is probably the most important. When you get good at it or you're comfortable, you probably will go with the simple beta. All right, next particle. Next particle is kind of the opposite. So a positron, it has the same mass as an electron, which is negligible. That's why it's a 0 up here, compared to a proton and neutron. But there is a small amount of mass. I should have said that about the beta too. But it has the opposite charge. It's a +1. It's a +1. So as a beta, neutron changes to a proton. When a proton changes back to a negative or to a neutral neutron, this positron is emitted, and that's what it looks like. Again, it's the mass of an electron, but it has the opposite charge of an electron, so we call it a positron. And again, it comes from the nucleus. All right, the last particle that we're going to talk about is gamma. So gamma is a ray. It's not a particle. It is an actual, and what is ray? It's an energy form, so it's pure energy. It's not, it doesn't have mass. Pure energy. It's electromagnetic radiation. We've talked about gamma before. We had gamma as being the most energetic of the electromagnetic spectrum, and then we went from gamma to X-rays to ultraviolet. So remember that part. This is all reviewed. This is so gammas are highly energetic. They pass through paper, plastic. It takes a fair amount of lead or concrete to stop or attenuate the energy of a gamma radiation. They have the most penetrating power of radiation, and they're symbolized by this gamma symbol here. So what you notice, there is no mass number, there's no atomic number. This is just pure energy, pure radiation. So if you don't see a change in the isotope in its mass or its number of protons, then gamma is going to be the telltale sign. I mean, those things will be the telltale sign to know that you're dealing with gamma radiation. So just because it's radiation doesn't mean that it's ionizing, that's going to knock electrons off and cause cancer and anything like that. Radiation can be a mechanical energy, like my voice, which is a mechanical wave which compresses and expands gas molecules. Excuse me. And then we have like visible light, which is not an ionizing form. It's not knocking electrons off of things. So the only three ionizing radiations that we're going to talk about is the alpha, which is the lowest, does the least amount it has the least amount of ionizing energy, then the beta, and then the gamma is the most. So gammas will do the most ionizing damage. Alpha would do the least. So we want to be able to write a nuclear equation of what's happening. So a nuclear equation has to be balanced in mass and number of protons. So again, the sum of the mass numbers on each side of the reaction arrow must be identical, and the sum of the atomic numbers on each side of the reaction arrow must be identical. If they're not, you've made a mistake. All right? So mass has to be conserved. We know the law of conservation of mass. Mass cannot be created or destroyed in a chemical reaction. Well, in a nuclear reaction, mass should not be, for the most part, not be created or destroyed. Sometimes mass is converted to energy using E equals mc squared, so it can be converted, but for what we're doing, they should be identical on both sides of the reaction arrow. Here's what it looks like. We have an isotope of uranium, so you would speak this as uranium-238. And we have a reaction arrow, and on the product side we have thorium-234, and we have a helium-4, or which we would call an alpha particle. So you see why you would rather write it this way than this way, because this gives you more information. So now you can see the 4 plus the 234 equals 238, so that part's correct. And 2 plus 90 gives me 92, so that part's correct. So we know that we've written this correctly, and you could be asked to write the chemical symbol here. And you could do that if you know the atomic number. You can look on the periodic table and find the chemical symbol. You could be given a blank here and say what type of ionizing radiation was emitted, and you could figure that out, that 238 minus 234 is 4, and 92 minus 90 is a 2, so I got 4 over 2, which is an alpha particle. So that's the type of questions you could see about when doing a nuclear equation, or an alpha decay in this case. All right, let's look at a beta decay. It's going to look different. So beta decay is that you start with an isotope or a nuclide, and let's say they didn't give us this part here. Well, the mass number did not change, so that tells us this is a 0 here. 16 minus 16 is 0. And then 7 minus 8 gives us a negative 1. 7 minus 8 gives us a negative 1. So knowing that that's a negative 1 and it's 0 for the mass number, we know this is a beta particle. This is a beta decay. So the telltale sign is, notice the mass number does not change, only the atomic number is changing. And that gives you an indicator that we're either dealing with a beta decay or a positron decay. But when I say 7 minus 8 and I get a negative 1, that tells me it's a beta decay. All right, let's look at a positron. Some of you may be doing positron emission tomographies to find out if a patient has cancer in their body. And so what this looks like is, again, if we didn't have this present, you can see again the mass number is not changing, but 6 minus 5 means this has to be a positive 1. So that positive 1 plus 5 gives me 6. So this is not beta because I have a positive 1 where the atomic number is. But I have a 0 up here for the mass number, so it's like an electron with a positive charge, and we call that a positron. So that's how I figured this out, that it's a positron. Once I figure it out, I may just write beta. I might write this for my symbol for the positron. Instead of writing an E, I might actually use a beta with a positive 1 there. This is not difficult. It's more about just being very careful and very aware of what you're doing and correcting your mistakes, and just making sure these numbers add up. 11 minus 11 is 0. 6 minus 5 is a positive 1. And then recognize that's a positron, not a beta particle. And then the easiest one is the gamma. So the gamma, nothing changes. It looks like nothing changes, all right? So it's 99, 43. 99 for the mass number, 43 for the atomic number. It's still 99, 43. But gamma radiation has been emitted. So where did the radiation come from? Well, notice this M stands for metastable. That means it's not. It's kind of like on top of this ladder, and it's teetering. And then all of a sudden the ladder falls. Well, the ladder's still there, but it's lost energy. That energy it lost was the gamma radiation. So gamma emits radiation that's got the most energy, it's most penetrating power, and what we see is the mass number and the atomic number does not change. So that's what makes it easy to identify. If nothing changes on one side of the reaction arrow to the other, then you know it's a gamma emitter. All right, so this is the type of problem you're going to see in your homework. If you can handle this homework, you're in great shape. I think Chapter 9 is real easy. It is a chance to bring up your grade. So here's what they do. They don't tell us what this is, X is. But here's what I know. 0 plus this mass number has to equal 239. So I know the mass number is 239. -1 plus this number has to equal 92. So this has to be 93. So 93 minus 1 gives me 92. So now that I know it's 239 over 93, I've got these two numbers. I look to the periodic table and find the chemical symbol, which is Mp, which is neptunium. Do I expect you to know all these names? No, I don't. But I do expect you to be able to look at the atomic number and be able to find the chemical symbol in the periodic table that represents that. All right. That's it for chapter 9. I think we go 9.1 and 9.2 here. And that's it for the content of this course. If you can handle this material in chapter 9, you're in good shape. So again, our last test before the final is over chapter 7, 8, and 9. And then you'll also see this chapter again on the final, because the final's comprehensive. I hope that helps. And if you have questions, just email me. Thank you.